Welcome, dear friend, to Dreams of Gravity. If you found your way here tonight, you've come to the right place. This is a space, quite literally, set aside for you to slow down, to breathe, and to let your mind wander somewhere vast and quiet and beautiful. Before we begin, I'd like to ask you to do something small. If you're still sitting upright, go ahead and lie down now, or settle into whatever position feels most comfortable for your body. Let your shoulders drop, unclench your jaw, rest your hands somewhere loose and easy. Let your legs go heavy. Notice the weight of your own body, the way the surface beneath you is holding you up, the way you don't have to do anything to stay here. Gravity is doing that for you, quietly and without effort. The same gravity that holds the planets in their orbits and pulls rivers toward the sea. You don't have to hold anything tonight. Take a breath in, nice and slow, and let it out. There's nowhere to be right now. Nothing to finish, nothing to figure out. The emails, the tasks, the thoughts that have been circling in the background of your mind all day. You can set those down. They'll be there tomorrow if you need them. But tonight, this hour belongs to you. Tonight, the only thing you need to do is listen. And even that you can do softly, without effort, the way you listen to rain on a window or wind moving through trees. Let the words come to you. Let them arrive at their own pace, like light that has been traveling for a long time and is only now reaching you. Tonight, we're going to travel somewhere, not with our bodies. Our bodies stay here, warm and still and resting, but with that quiet, curious part of the mind that never really stops wondering. We're going to travel out into the universe, into the deep, dark, extraordinary cosmos that surrounds us every moment of our lives, whether we think about it or not. A universe full of things so strange and so beautiful that even the scientists who dedicate their entire lives to studying it still regularly look up and say, simply, I don't know. And there is something deeply comforting about that, don't you think? That the universe is bigger than any one answer. That mystery isn't a problem to be solved, but a place to rest inside of. That we are not required to understand everything in order to be moved by it. A child standing at the edge of the ocean doesn't need to know marine biology to feel something enormous and true in that moment. The feeling itself is enough. So let's begin. Gently, slowly, like stepping into a warm, dark ocean. Close your eyes if that feels right. The journey is already starting. Imagine, for a moment, that you could step outside. Not just outside your front door, but outside everything. Outside the city, outside the atmosphere, outside the thin blue shell of sky that wraps around our little world. Imagine rising up through the clouds, then past them, into the cold silence above. The stars appear one by one, and then all at once, thousands of them, scattered like light through water, like phosphorescence in a midnight sea. You float there for a moment, weightless, looking back at Earth. A small marble of blue and white, patient and quiet, orbiting an ordinary yellow star at the edge of a galaxy that stretches 100,000 light years across. That's where you live, on that blue dot. Tucked into one spiral arm of the galaxy we call the Milky Way, which itself is one of roughly 2 trillion galaxies in the observable universe. 2 trillion. It's the kind of number that doesn't really mean anything when you first hear it, does it? Our minds weren't built to feel numbers that large. But let yourself sit with it for a second. 2 trillion galaxies, each containing hundreds of billions of stars, each of those stars potentially orbited by planets, and many of those planets possibly holding conditions that could support life. The universe is not empty. It is overflowing with structure and light and motion and quiet cosmic processes happening right now in this very moment as you lie here in the dark. The light you see when you step outside at night, those faint points scattered across the sky, represents only a tiny fraction of what is actually out there. Most of the universe is too far away, too faint, or shining in wavelengths of light that human eyes cannot see. There are entire galaxies that have never been observed because no telescope has yet been pointed in their direction long enough to gather their light. The universe, in that sense, is like a library with billions of books and only a handful of lamps. We read what the light allows us to reach. By the way, I wonder, just briefly, where are you watching from tonight? Which city are you in right now, and what time is it for you? Is the night deep where you are, or are you drifting off in the early hours of an evening? There's something I love about that. The idea that somewhere, someone is listening to this under a sky that's just turning dark, and someone else is listening at 3 in the morning when the world has gone completely still. You're all out there, scattered across the map, and yet we're all looking up at the same stars. That thought always makes me feel less alone. But let's keep moving. The universe is patient, and there is so much to see. Galaxies, islands in the darker galaxy, is, at its most basic, a gravitational family. A collection of stars, gas, dust, and something we call dark matter. More on that later, all held together by gravity, slowly spinning through space like a slow-motion pinwheel. The Milky Way, our own galaxy, is shaped like a flat spiral disk with a bulging center. And it takes our solar system about 225 million years to complete one full orbit around that center. The last time Earth was in this exact position along its galactic journey, dinosaurs had only just begun to appear. We call that span of time a cosmic year. One cosmic year. 225 million of our years, wrapped up into a single orbit around the center of the Milky Way. Let that settle for a moment as you breathe. Our nearest large galactic neighbor is called Andromeda, and it's heading toward us. Slowly, gracefully, inevitably. In about 4.5 billion years, the Milky Way and Andromeda will meet and merge into a single massive galaxy. This collision will not be a catastrophe in the way we usually imagine collisions. The two spirals will pass through each other, their stars spread so far apart that almost none of them will physically collide. They'll simply swirl together, gravity pulling them into a new shape, a new home, over hundreds of millions of years. Astronomers have even given this future galaxy a name. They call it ʻOumuamua. Somewhere in that merged galaxy, if any version of Earth still exists, someone might look up at a sky filled with two great rivers of stars instead of one. Imagine that sky, the whole arc of the merged galaxy blazing overhead, a band of light so thick and bright it would cast faint shadows on the ground on a clear night. A sky full of history written in light. But even within our own galaxy, the variety is extraordinary. There are galaxies shaped like spirals, like ellipses, like lenses, like irregular clouds of light with no clear shape at all. There are starburst galaxies, regions where stars are forming at a frantic rate, hundreds of times faster than in our own Milky Way, pouring out so much energy they outshine everything around them. There are galaxies that have been tidally disrupted by larger neighbors, their spiral arms stretched into long ribbons of stars trailing through space like hair in slow-moving water. There are ring galaxies, formed when a smaller galaxy punches directly through the center of a larger one, sending a ripple of star formations spreading outward like a wave from a stone dropped in a pond. There are also galaxies that seem to have almost no stars at all. Ghost galaxies, sometimes called ultra-diffuse galaxies, spread over enormous areas of space, but containing so little luminous matter they are nearly invisible. They are held together almost entirely by dark matter, ghostly scaffolding with almost nothing hanging on it. We've only recently begun to discover them, and each one raises more questions than it answers. The universe organizes itself, even across distances so vast they make the mind go soft. There is structure. Galaxies gather into clusters, clusters gather into superclusters, and superclusters are arranged along enormous filaments of dark matter, long web-like strands that stretch across hundreds of millions of light years, forming what scientists call the cosmic web. If you could step back far enough to see the whole observable universe at once, it would look like a vast, shimmering network of light, not unlike the neurons of a brain, or the roots of an ancient tree, or the foam of a wave just as it breaks. We are part of a pattern, a beautiful, incomprehensible, quietly breathing pattern that was set in motion 13.8 billion years ago and has never stopped unfolding. Stars, the furnaces of creation. If galaxies are the islands, then stars are the lights burning in every window. A star is born in the cold, dark clouds of gas and dust that drift between the stars. Nebulae, we call them, which is the Latin word for mist or fog. Deep inside these clouds, where gravity is patient and persistent, tiny regions slowly begin to collapse inward. The gas gets denser, warmer. It begins to spin because even the tiniest hint of rotation is amplified as material falls inward. The way a skater spinning slowly with arms wide will speed up when they pull their arms in. The collapsing cloud forms a disk, rotating faster and faster, with a hot, dense knot of material growing at the center. And eventually, over hundreds of thousands of years, that central knot becomes hot enough that something extraordinary happens. Hydrogen atoms, pressed together under enormous pressure and heat, begin to fuse into helium. And in that fusion, a tiny fraction of mass is converted directly into energy. Light, heat, radiation. A star ignites. This process, nuclear fusion, is the engine of the universe. It is the same process that lights up the sun that warms your face on a summer afternoon. Every photon of sunlight that has ever touched your skin was born deep inside the core of the sun, produced by hydrogen atoms being crushed together. And here is the part that I always find quietly astonishing. A photon of light can take up to 100,000 years to travel from the core of the sun to its surface, bouncing, absorbed, re-emitted, absorbed again, step by slow step through the dense solar interior. And then, once it finally reaches the surface, it crosses the 93 million miles between the sun and Earth in just 8 minutes. 8 minutes. To cross 93 million miles. You are warmed by light that began its journey before humans walked the Earth, before Neanderthals, before our entire genus existed. Light that fought its way slowly, photon by photon, through the body of a star, and then flew in less time than it takes to make a cup of tea to rest gently on your skin. Stars live long lives by human standards, but they are not eternal. Our Sun is middle-aged at about 4.6 billion years old, with roughly another 5 billion years left to burn. Smaller stars, red dwarfs, cool and dim and miserly with their fuel, can burn for 1 trillion years or more. Some of the smallest red dwarfs that formed in the early universe are still burning today, unchanged, while civilizations rose and fell and galaxies merged around them. They are the tortoises of the cosmos, unhurried, patient. But larger stars, stars many times more massive than our Sun, live fast and die spectacular deaths. A star 10 or 20 times the mass of the Sun might burn brilliantly for only a few million years before exhausting its fuel. Without the outward pressure of fusion to balance gravity, the core collapses in a fraction of a second, and the outer layers, falling inward, hit the collapsing core and bounce back outward in a titanic explosion. A supernova. A single supernova can, for a brief period, outshine an entire galaxy of hundreds of billions of stars. It is the brightest thing in the universe, a momentary blaze of energy that can be seen across billions of light years, announcing in light the death of one star and the beginning of everything that death makes possible. Because supernovae are factories. In the crushing pressure of a stellar core at the moment of collapse, elements are forged that could never exist inside a star's normal burning. Gold, silver, platinum, uranium. These heavy elements are scattered across space in the explosion, drifting and dispersing through the interstellar medium, eventually incorporating into new clouds of gas and dust, new generations of stars, new planets, new life. The calcium in your bones was forged in the heart of a star that lived and died before our Sun was born. The iron in your blood was scattered across space in a supernova explosion billions of years ago, drifting through the void until gravity slowly gathered it, step by step, into a cloud, then a disk, then a planet, then eventually, through chemistry so intricate it still isn't fully understood, into life, into cells, into you lying here in the dark, breathing slowly, made of the debris of ancient stellar explosions. You are not just looking at the universe. You are the universe, looking at itself. Planets, the quiet travelers. Orbiting these stars are planets by the billions. We used to think our solar system was unique, perhaps even special. Now we know better. In recent decades, astronomers have discovered thousands of exoplanets, planets orbiting other stars, and the evidence suggests that most stars have at least one planet. Some have many. Our galaxy alone may contain more planets than it does stars. They come in astonishing variety. There are hot Jupiters, gas giants larger than our own Jupiter, orbiting so close to their parent star that a year lasts only a few Earth days, their outer layers being slowly burned away into space, leaving long comet-like tails of evaporating atmosphere. There are ocean worlds, planets covered entirely by deep, dark seas, with no land above the waves, water going down tens or hundreds of kilometers before reaching any solid floor, with pressures so immense that water at the deep bottom exists in exotic forms of ice that cannot melt, pressing upward against the liquid water above. There are lava worlds, their surfaces entirely molten, glowing faint orange from space. There are ice giants like Neptune and Uranus in our own solar system, worlds where it may rain diamonds in their deep interiors, where carbon is compressed so thoroughly that it crystallizes and falls as glittering stones through layers of liquid. There are rogue planets, worlds that have been flung out of their home solar systems by gravitational interactions and now drift through interstellar space with no star to orbit at all, cold and dark, heated only by the faint glow of radioactive decay in their cores, and perhaps, if they are large enough, by the slow compression of their own gravity. And among all these worlds, certain ones sit inside what astronomers call the habitable zone, that region around a star where liquid water could exist on a surface. Not too hot, not too cold. The Goldilocks zone. Earth sits comfortably inside ours. But here is a thought worth carrying as you begin to drift tonight. The universe is 13.8 billion years old. Earth formed about 4.6 billion years ago. That means that for more than 9 billion years before Earth existed, stars were burning, planets were forming, and the habitable zones of older stars were doing whatever habitable zones do when given enough time. There are stars out there far older than our Sun, with rocky planets that have been sitting in their habitable zones for billions of years longer than Earth. If life can arise on a planet, and we know it can, because here we are, then what might arise on a planet that's had twice as long? The question of whether we are alone in this universe is one that science has not yet answered. But the numbers suggest that solitude at a cosmic scale would be the real surprise. Somewhere, perhaps, under an older sun, on a world we have not yet found, something is also looking up, also wondering, also breathing slowly in the dark and asking itself the same quiet questions we ask ourselves tonight. Black holes, where the universe keeps its secrets. And now we arrive at the place where the universe stops playing by the rules we know, or rather, where it plays by rules so extreme that our familiar intuitions dissolve like morning mist. Black holes. A black hole is what remains when a massive star collapses at the end of its life, and nothing, no force in nature, can stop the collapse. The core is crushed inward, past the density of an atomic nucleus, past any state of matter we have a name for, compressed into a point of essentially infinite density, a singularity. And around that point, space and time themselves are so warped by gravity that nothing, not matter, not light, not information of any kind, can escape past a certain boundary. We call that boundary the event horizon. The event horizon is not a physical surface. If you were to fall through it, you would feel nothing unusual in that instant. You would cross it as easily as crossing an invisible line drawn in the air. But once crossed, there is no going back. All paths through space and time, every direction you could move, every choice you could make, lead inward. The singularity is not ahead of you. After crossing the horizon, the singularity is in your future, the way Tuesday is in the future. Inescapable not because of walls, but because of the structure of time itself. What happens beyond the event horizon, we cannot say. Our equations, our best, most carefully tested physics, return infinities and paradoxes when applied there. The honest answer is that we do not know, and we may never know because nothing that crosses that boundary can ever come back to tell us. There is a saying among physicists that black holes are where the laws of physics go to die, though perhaps it would be gentler to say they are where the laws we know give way to laws we have not yet found. Stellar black holes, born from individual supernova explosions, can be a few times the mass of our Sun compressed into an object smaller than a city. But then there are the giants, supermassive black holes. At the center of almost every large galaxy in the universe sits one of these behemoths, millions or billions of times the mass of an ordinary star, accumulated over cosmic time through the merging of smaller black holes and the swallowing of vast amounts of gas and stellar material. The supermassive black hole at the center of our own Milky Way is called Sagittarius A star. It contains the mass of about 4 million suns, compressed into a region smaller than the orbit of Mercury. It sits at the galactic center, about 26,000 light-years away from us, surrounded by a cluster of stars orbiting it at dizzying speeds, some completing full orbits in just a few years, racing around their invisible master at millions of miles per hour. And then there are the true giants. The black hole at the center of the galaxy, 87, the one photographed by the Event Horizon Telescope in 2019, contains the mass of 6.5 billion suns. It is so large that our entire solar system would fit within its event horizon many times over. The image taken of it, that soft orange ring of glowing gas around a dark shadow, required a telescope the size of the entire Earth, 8 radio observatories on different continents coordinated to work as one, and 2 years of computing to produce. When that image was released, many of the scientists who had dedicated years of their lives to the project were in tears, because they had seen the unseeable. They had taken a photograph of an edge. There is also something called a quasar, a phenomenon from the early universe where a supermassive black hole is actively devouring enormous amounts of gas. As the gas spirals inward, it forms a superheated disk that glows with the energy of trillions of suns. Quasars are the brightest sustained objects in the universe. Some are so luminous they can be detected across almost the entire observable universe, and they are powered by nothing more than gravity and falling gas, a black hole eating and in eating, lighting up the cosmos. The most luminous quasar known releases energy equivalent to about 600 trillion suns. From a safe distance, it would blaze in the sky like a second sun, even across billions of light years. That image, a black hole at the center of the cosmos, blazing with the fire of things it consumes, surrounded by dark, might be one of the most honest portraits the universe has ever painted of itself. Everything in it, the consumption, the light, the darkness, the edge beyond which we cannot see. Neutron stars, the densest objects we can measure. Before we drift further, let us pause on something smaller than a black hole, but no less astonishing. When a star not quite massive enough to form a black hole reaches the end of its life and its core collapses, it can form something called a neutron star. A neutron star is what remains after a supernova explosion strips away the outer layers. A sphere roughly 20 kilometers across, containing between 1 and 2 times the mass of our Sun, compressed so tightly that the electrons and protons of atoms are crushed together into neutrons. The entire object is, in essence, a single enormous atomic nucleus. A teaspoon of neutron star material would weigh about 10 million tons. If you were to hold a sugar cube of it in your hand, which you could not for many reasons, it would weigh more than all the mountains on Earth combined. Neutron stars spin. They spin very fast because the same physics that makes an ice skater spin faster when they pull in their arms applies when an entire star collapses into a sphere 20 kilometers wide. Some neutron stars spin hundreds of times per second. We call these pulsars, They beam radio waves or X-rays from their magnetic poles as they spin, and we detect those beams as regular pulses, as reliable as a lighthouse in a storm. The most precisely spinning pulsars keep time better than atomic clocks. Some pulse over 700 times per second. The first pulsar was discovered in 1967 by a young graduate student named Jocelyn Bell Burnell, who noticed a strange, impossibly regular signal in her radio telescope data. The signal was so precise, so metronomic, that she and her colleagues briefly labeled it LGM1 for Little Green Men. They genuinely considered the possibility that it might be artificial, a beacon from an intelligent civilization. It was the first time the possibility of extraterrestrial contact felt, to trained scientists, briefly real. It turned out to be something entirely natural and arguably just as strange. Nebulae, the nurseries and graveyards of stars. Between the stars, filling the spaces where light grows thin and the darkness deepens, there are clouds. Great clouds of hydrogen gas and dust, glowing in colors no human eye has seen directly, because many of them glow in wavelengths of light beyond our visual range. It takes special cameras, patient telescopes, and long exposures to reveal their colors to us. Deep reds and purples from hydrogen, cool blues and greens from doubly ionized oxygen, warm golds from nitrogen. When the Hubble Space Telescope brought back images of these regions, the pillars of creation, the Crab Nebula, the Helix Nebula, the Butterfly Nebula, the Orion Nebula, it was as though someone had shown us a part of our own home we had never seen before. Something that had always been there, vast and silent, surrounding us at distances we couldn't imagine. The pillars of creation are perhaps the most famous of these images. 3 towering columns of gas and dust rising inside the Eagle Nebula, about 6,500 light-years away. Each pillar is several light-years tall. If you wanted to fly from the base of one pillar to its tip at the speed of light, it would take years. They are regions where new stars are actively forming right now, deep inside those dense clouds, gravity pressing gas into future suns, with the patience of something that has all the time in the universe. Here is a strange and slightly melancholy footnote to that image. Astronomers believe the pillars of creation may have already been destroyed. A supernova explosion nearby is estimated to have obliterated them about 6,000 years ago. But because light takes time to travel, we are still seeing the pillars as they were 6,500 years ago, standing intact, lit by starlight, serenely beautiful. The news of their destruction is still on its way to us. In about 1,000 years, the night sky will change in that region as the shockwave and the aftermath of the explosion finally reach us. We are, in a sense, looking at a photograph of something that no longer exists. This is not unique. Much of what we see in the night sky is memory. Light that left its source before any human civilization existed, before agriculture, before written language, arriving now at your eyes as though delivered by a messenger from a world that may have changed beyond recognition in the time the message was in transit. Nebulae are also where stars end. When a star like our Sun exhausts its hydrogen fuel and swells into a red giant, expanding to engulf the inner planets, glowing orange and enormous in the sky of whatever outer worlds survive. It will eventually shed its outer layers in a slow, graceful exhalation. The gases drift outward, forming a slowly expanding shell, lit from within by the ultraviolet radiation of the star's exposed core. A planetary nebula, a last breath made visible. These dying stars are among the most beautiful objects in the known universe. The Helix Nebula looks so much like an enormous eye staring outward from the cosmos that it has been nicknamed the Eye of God. The Butterfly Nebula spreads its wings of hot gas at temperatures of more than 20,000 degrees across 2 light-years of space. The Ring Nebula, a near-perfect circle of glowing gas surrounding a small white star, hangs in the constellation Lyra like a smoke ring blown by a gentle giant. And at the center of each of these, quietly cooling, sits what remains of the star, a white dwarf, a diamond-like remnant of carbon and oxygen, no larger than Earth, but containing about half the mass of the original star. Over billions of years, over timescales that make the current age of the universe look brief, it will cool from white to yellow, to orange, to red to black. A cold, dark cinder drifting through space, carrying no more light. That is what our sun will become in about 8 billion years. A small, cooling ember surrounded by the faint, fading ghost of its final breath. There is nothing tragic in this. It is simply the rhythm of the universe. Breathing in, breathing out. Stars born from clouds, stars returning to clouds. The same atoms recycled endlessly, wearing different forms across incomprehensible spans of time. Time, the river that runs through everything. Let's talk about time. Because time in the cosmos does not work the way we experience it in our daily lives. Here on Earth, time feels constant. A second is always a second. We trust it so completely that we build entire civilizations around its regularity. But Einstein showed us more than 100 years ago that time is not constant at all. It is relative. It bends. It stretches and compresses depending on where you are and how fast you're moving. Time passes more slowly in strong gravitational fields. This is called gravitational time dilation. If you were to stand on the surface of a neutron star, where gravity is hundreds of billions of times stronger than Earth's, time would crawl by for you while racing ahead for someone floating in empty space far above. An hour on the neutron star's surface might correspond to far longer in the outside universe. This is not a thought experiment. It has been measured here on Earth, with atomic clocks flown on airplanes, placed at different altitudes, carried around the planet. Time at sea level runs slightly slower than time at the top of a mountain. The GPS satellites we use every day must account for relativistic time differences to give accurate positions. Without corrections for relativity, GPS would drift by miles within a day. Einstein's equations also tell us that time passes more slowly when you are moving very fast. The faster you move through space, the slower you move through time. A traveler moving at a significant fraction of the speed of light would return from a journey to find that far more time had passed on Earth than for them. This effect is real. Muons, tiny particles created in the upper atmosphere when cosmic rays hit air molecules, travel so fast that time passes for them at a fraction of the rate it does for us on the surface. They should decay before reaching the ground. They don't, because from the perspective of their own brief existence, they're barely aging. We detect them, and in doing so, we confirm that time can be stretched thin by speed. Near a black hole, these effects become dramatic and surreal. As you approach the event horizon, time, from the perspective of a distant observer, slows to a crawl. A clock falling toward a black hole would appear to tick more and more slowly from outside, the signals it sends becoming more and more stretched, red-shifted toward longer and longer wavelengths. The falling clock appears to slow and freeze, its final moment stretched into eternity, the light from it becoming dimmer and redder until it fades entirely. What does time mean inside a black hole? Our current mathematics cannot say. Perhaps, in there, time and space exchange roles in ways we have no words for. Perhaps time ends there, and something else begins. These are not science fiction questions. They are legitimate, open questions in theoretical physics. There is another way that time becomes strange in the cosmos, and this one is simply poetic. When you look at the night sky, you are not seeing it as it is. You are seeing it as it was. Light from the nearest star beyond our sun takes 4.2 years to reach us. Light from the center of the Milky Way takes 26,000 years. Light from the Andromeda Galaxy takes 2.5 million years. Light from the most distant galaxies visible to our best telescopes has been traveling for more than 13 billion years. Every point of light in the sky is a message from the past. And the sky we see, the entirety of it, all those stars and galaxies layered at different distances, is a kind of temporal collage, a patchwork of moments from different epochs of cosmic history, all arriving at your eyes at the same instant. The star next to the galaxy, next to the nebula in your field of view, might represent moments separated by billions of years. You are, when you look up, an archaeologist of light. You are reading a history written in photons, and the book is still being written right now in every direction at the speed of light. Dark matter and dark energy. The invisible majority. Here is a quiet fact that tends to make people pause. Everything we have ever seen, studied, measured, or touched, every atom of every star, planet, moon, nebula, black hole, and human being, accounts for only about 5% of the total content of the universe. 5%. The other 95% is made of two things we do not understand. We call them dark matter and dark energy, though these names are really just placeholders. The scientific equivalent of writing here be dragons on an old map. Dark matter makes up about 27% of the universe's total energy content. We know it exists because of how galaxies behave. The stars at the outer edges of spiral galaxies orbit the galactic center much faster than they should, given the amount of visible matter present. If you calculate the mass of a galaxy from the stars and gas you can see, and then calculate how fast the outer stars should orbit based on that mass, you get numbers much smaller than what we observe. Something is providing extra gravitational pull. Something massive, spread throughout and around galaxies, invisible to every kind of telescope we have. Dark matter does not emit light. It does not absorb light. It does not interact with ordinary matter except through gravity. It passes through you, through the Earth, through the Sun, in an unceasing, unfelt stream. Billions of dark matter particles crossing through your body every second, leaving no trace. We know it must be there, and we cannot find it. Decades of experiments in deep underground laboratories designed to catch the faint recoil of a dark matter particle bouncing off an atomic nucleus have found nothing. The universe's majority ingredient remains stubbornly invisible. Dark energy is stranger still. It makes up about 68% of the universe, the single largest component of everything. and it appears to be a property of space itself, a kind of gentle pressure built into the very fabric of the cosmos. And this pressure is causing the universe to expand faster and faster with every passing moment. The more space there is, the more dark energy there is, and the faster things accelerate apart. This was discovered in 1998 by two independent teams of astronomers studying distant supernovae. They expected to find that the expansion of the universe was slowing down, decelerated by gravity over cosmic time. Instead, they found it was speeding up. The discovery was so unexpected that the lead scientists thought at first they had made an error. They had not. Both teams won the Nobel Prize. And the universe remains mysterious. The universe is not just large, it is growing. Right now, as you lie here in the dark, the space between distant galaxies is expanding. Galaxies far enough from us are receding faster than light, not because they are moving through space faster than light, but because the space between us and them is growing so rapidly. We can never reach them. We can never communicate with them. They are, in the most complete sense, forever beyond our reach. And the observable universe, the region from which light has had time to reach us since the Big Bang, is not a boundary we can one day cross. It is, in a profound sense, the edge of our world. Everything beyond it is as unreachable and unknowable as the inside of a black hole, but for an opposite reason. Not because of too much gravity, but because of too much space. The size of everything. An ocean without shores. Let me try to give you a sense of scale. The Earth is about 12,700 kilometers across. The Sun is large enough to contain about 1.3 million Earths. The distance between the Earth and the Sun is about 150 million kilometers. A distance light covers in 8 minutes. Traveling at the speed of a commercial airplane, you would take about 19 years to reach the Sun. The nearest star beyond our Sun, Proxima Centauri, is about 4.2 light-years away. Our fastest space probe, Voyager 1, launched in 1977, has traveled for nearly 50 years and covered about 0.002 light-years. At that speed, it would take roughly 73,000 years to reach our nearest stellar neighbor. The Milky Way galaxy is about 100,000 light-years across. The Andromeda galaxy is 2.5 million light-years away. The Virgo cluster, the nearest large cluster of galaxies, of which the Milky Way is a distant outlying member, is about 65 million light-years away. The observable universe, the sphere of space from which light has had time to reach us, is about 93 billion light-years in diameter, and we don't know if the universe ends there. Evidence suggests the universe may be flat and infinite, stretching in all directions forever, filled endlessly with galaxies and stars and dark matter and dark energy, beyond any horizon, beyond any possible knowledge, an ocean without shores. And in the middle of all of this, here you are, warm, still, breathing, on a rock orbiting a star in the outer arm of a spiral galaxy, in a universe so vast it does not have an edge anyone has found. It seems almost too small to matter from one angle. From another, the one I prefer on quiet nights, it seems extraordinary, because out of all that vastness, this tiny corner of it somehow arranged itself into awareness, into wonder, into the capacity to look up and ask, what is all of this? Infinity and the nature of everything. The universe began about 13.8 billion years ago in an event we call the Big Bang. Not an explosion in space, but an expansion of space itself from an unimaginably hot and dense state. In the first fraction of a second, the fundamental forces of nature separated. Quarks combined into protons and neutrons. In the first 3 minutes, those combined into the nuclei of hydrogen and helium. For the next 380,000 years, the universe was too hot and dense for atoms to form. It was an opaque plasma, like the interior of a star, light unable to travel freely. And then, 380,000 years after the beginning, the universe cooled enough for electrons to settle into orbits around nuclei. Atoms formed. And the universe became transparent. Light flooded through for the first time, traveling freely in all directions. That first light is still traveling today, stretched by the expansion of the universe from visible light into microwave radiation, detectable in every direction as a faint, uniform glow filling the entire sky. We call it the cosmic microwave background. It is the oldest light in the universe. The echo of the moment everything began to be visible. From that point, gravity began its long, patient work. Tiny fluctuations in the density of the early universe, quantum variations from the very beginning, stretched to cosmic scales by inflation, became the seeds of structure. Over millions of years, hydrogen clouds collapsed into the first stars. Over hundreds of millions of years, the first galaxies assembled. Stars lived and died and scattered their elements into space. New generations formed, richer in heavy elements, with planets circling them. And on at least one of those planets, after 4 billion years of chemistry and biology, something looked up at the sky and wondered where it had come from. We are 13.8 billion years of cosmic history, compressed into a body that breathes and thinks and feels, and occasionally, at the end of a long day, needs to lie down and rest. And the future stretches out in directions that are immense and quiet to contemplate. Our sun will burn for another 5 billion years. The Earth will likely be consumed when the sun expands into a red giant. Over trillions of years, the last stars will cool and go dark, one by one, across timescales that dwarf the current age of the universe. Black holes will slowly evaporate over incomprehensible eons through a process called Hawking radiation, emitting tiny amounts of energy, so slowly that the last black holes won't finish evaporating for perhaps 10 to the power of 100 years. And then, a silence so complete, so final and so far away that it barely belongs in the same thought as tonight. Because tonight, the universe is young. It is bright and busy and full of motion. Galaxies are forming. Stars are being born. Somewhere, right now, a planet is cooling into something that might one day hold an ocean. The universe is nowhere near finished. It is in its early chapters. And you are here, in the middle of it all, still and warm and breathing, part of a story that started before time had a name. The space within one last thought, before we let the night take over completely. The universe is large. We've established that. But here is something that doesn't get said often enough. The universe is also mostly empty. Atoms, the building blocks of all matter, are themselves almost entirely empty space. A hydrogen atom consists of a proton in the center and an electron in a cloud of probability orbiting around it. If you scaled the proton up to the size of a marble and placed it in the center of a large sports stadium, the electron's orbit would extend somewhere beyond the outer walls. everything in between, all of that space is empty. No matter, no substance, just the invisible fields of force that hold the whole arrangement together. The matter in your body, compressed to eliminate all the empty space within and between its atoms, would fit in a space smaller than a grain of rice. Your atoms are almost entirely emptiness, held in shape by forces we can describe mathematically but cannot truly picture. Which means that you, reading this, breathing this, warm and solid and entirely real, are made of something that is, at its foundation, almost nothing. And the chair beneath you, the floor beneath that, the bedrock of the earth, all of it at the atomic level is mostly space. The solidity we feel is the electromagnetic repulsion between the outer electrons of atoms, not any kind of true contact. Nothing in the universe ever truly touches anything else. Everything is force and field and probability, dancing in the dark. And yet, out of this near-nothingness, the universe has assembled warmth and color and music and memory and love and curiosity and all the 10,000 things that fill a human life. From almost nothing, from particles so small they have no size we can measure, the universe has built mountains and oceans and neurons and laughter. You are made of almost nothing. And yet you are here, breathing, wondering, still here at the end of this long, quiet journey. Good night from the stars. The universe is wide open, and it is very old, and it holds more mysteries than answers, and that is exactly how it should be. There will always be more to discover, more dark corners of space that no human eye has ever seen. More signals arriving from galaxies so distant we haven't yet turned our telescopes in their direction. More questions that current physics cannot answer, waiting for someone not yet born to find the right way to ask them. That vastness isn't something to feel small inside of. It is something to feel held by. You belong to this, to the same universe that made the pillars of creation, and the rings of Saturn, and the aurora, and the deep ocean, and the sound of rain. You are not separate from any of it. You are it, looking at itself for a little while. So let the night do what the night does best. Let your thoughts drift like light across the dark, slow and warm and unhurried. Let the galaxies spin at their own pace. Let the stars burn on in the dark above you, as they have been burning since long before your name existed, and as they will burn long after the last trace of us has returned to the elements. Let the universe expand, quietly, in all directions at once, while you stay here, still and safe and exactly where you need to be. Dream of deep space and ancient light. Dream of oceans with no shore and stars being born in slow, silent clouds. Dream of the pulse of a neutron star ticking in the dark like a lighthouse for a ship that will never come. And the ring of orange fire around a black hole at the center of a galaxy 55 million light-years away. And the faint background glow of the first light, still traveling after 13.8 billion years. Still warm, still reaching every corner of everything. Sleep well, dear traveler. The stars will be here when you wake up. This has been Dreams of Gravity. Good night.